Ka and Kb for a weak acid and its conjugate base are related in this way. So if we know the Ka of a weak acid, we can calculate the Kb of its conjugate base. Now there are limits to calculating this. For example, if we have a strong acid, it doesn't really have a Ka. So its conjugate base we're going to consider does not have a Kb because it is such a weak base it won't take a proton from water. And then on the other hand, we have oxide, which is such a strong base that it cannot exist as oxide in water. As soon as it goes to water, it removes a hydrogen from water and exists as hydroxide. So there are some limits to this. So when we're looking at this relationship, we are basically looking at acids and bases that have Ka values, weak acids and weak bases. So let's look at a practice problem that allows us to use this relationship. So I'm going to choose this problem, 1682. The problem right before it, 1681, is very similar, and you can check the answers at the back of the textbook if you want to do another example of this on your own. So it tells us to use the data from Appendix D, calculate the concentration of hydroxide and pH for each of the solutions. So let's look at A, where we have 0.105 molar sodium fluoride. So if we look at what we have in solution, sodium and fluoride, remember that sodium is the conjugate base, the conjugate acid of a strong base, so it does not affect the pH. So what we're looking at in terms of affecting the pH and the concentration of hydroxide is fluoride. Now anions act as bases, usually, and this is how they act as bases. The fluoride is going to react with water, is going to take a proton from water to form the conjugate acid and hydroxide. So to calculate the concentration of hydroxide here, we're going to have to construct an ICE table. So we know that we begin with 0.105 molar fluoride, and we're going to assume that we have zero concentration of both hydroxide and HF. Now, we know to begin with we have 1 times 10 to the minus 7 molar hydroxide, but that's so small that we generally don't regard it. Since we have concentrations of 0 in our product, we know that the reaction has to shift to the right. So I'm going to lose my reactant, and I'm going to gain my product as the reaction moves to establish equilibrium. And because all my stoichiometric coefficients are 1 to 1, my x is going to have a coefficient of 1. So what I need to do now is fill in my bottom row of the ICE chart, which is just the sum of the first two rows. So at equilibrium, my concentration of fluoride is going to be 0.105 minus x, and my concentration of hydrofluoric acid and hydroxide are going to be equal to x and equal to one another. Now, to be able to solve for x, we need to know what our Kb value is. And here's the equilibrium expression, but we need an actual value for Kb. And here is Appendix D. Hydrofluoric acid is the conjugate acid of fluoride. And I'm not going to take, well, I actually could take you to the bases. So we look at where the bases are. I'm not going to find fluoride there. It's not, these are all in alphabetical order. Fluoride's not there. So what I have to do is I have to use the data for its conjugate acid. So hydrofluoric acid is the conjugate acid of fluoride, and here is its Ka value. So to calculate what the Kb for fluoride is, we're going to use this relationship. So Ka times Kb is equal to Kw, and of course this is for a conjugate acid and its conjugate base. We know what the Ka is for hydrofluoric acid based on Appendix D, 6.84 times 10 to the minus 4. So now what we have to do is we just have to use algebra. I'm going to divide both sides of the equation by Ka, and when I do that, the Ka over here will cancel out. And so Kb is going to be 1 times 10 to the minus 14th, so that's the value of Kw, divided by Ka. So when I plug that into my calculator, I get Kb is equal to 1.47 times 10 to the minus negative 11. So now that I have my Kb value, I plug it into my equilibrium expression, and now I just use algebra to simplify. Now I can be pretty sure that I can eliminate the x in my subtraction here because my Kb value is so incredibly small and my original concentration is relatively large. So I'm going to multiply both sides by 0.105 after I eliminate the x in my subtraction. And when I do, I'm going to multiply x by x to get x squared. And so then when I multiply 1.47 times 10 to the minus 11 by 0.105, I get 1.54 times 10 to the minus 12. And then I'm going to take the square root of both sides to get x. And then I get 1.24 times 10 to the minus 6 is equal to x. And so I want to be sure and check my 5% rule, even though I can clearly see that it's going to work here. And I get that this amount is way, way less than even 1%. So I'm okay in eliminating my x here in my subtraction. Okay, so I go back to my ICE chart, and now I have figured out one of the parts of the problem, which was determine the concentration of hydroxide. And according to our ICE chart, X is hydroxide, and I figured that out. Now the next part is calculating the pH. So there are several ways we can calculate the pH. I just like to calculate the pOH. So I take the negative log of the concentration of hydroxide, and I get 5.91. And then I remember that pH plus pOH is equal to 14. So pH is equal to 14 minus pOH, and so then I get my final answer. And of course, for my pH. And that makes sense because this is a basic solution, so my pH should be greater than 7.